See,
Hey David, how are you?
I'm doing fine. How you doing?
Doing good.
Math going?
It's going good.
Okay. So we're going to work on
I
logs tonight?
yeah, well, first of all, did we pay for the last session? Did you get the check?
I don't know.
It was a little while ago, I know that.
Let me see if I've got... I don't think I sent you an invoice, and you only owe $9, unless I haven't put one in here recently. Have you had a session since January 22nd?
I do not think so.
No, I think your balance is only 9. So when it gets to a reasonable number, I'll send out an invoice. I rarely do when it's below double digits.
Oh, okay, cool.
So
Yeah,
don't worry about it. I'll send an invoice when I need to be paid. So,
all right, cool.
okay. All right. Every discussion about logs needs to start here with y equals b to the x. This is an exponential expression. That is not an algebraic expression. That's an exponential expression.
Right.
What is the equivalent logarithmic expression to that?
Log of b, right? Or
I call it,
log of,
I'm not sure what the terminology your teachers use. I say log base b
log base b
of
y equals x.
Okay. The only thing you ever have to really remember is that logs are exponents. That's what they are. So if I forgot how to do this, I would immediately say, well, I know that the log has to be equal to x. Well, the b always goes down here, and there's only one place for the y right there.
Right.
So what's the logarithmic expression of 8 equals 2 cubed?
It's going to be log base 2 of 3 equals 8.
No, remember the log has to be equal to the exponent.
So the log base 2 of 8 equals 3.
There you go. Okay?
Yeah.
So, being able to go back and forth between these two things, that's the most important skill you can have in logarithms. Is always be able to...
I get those mixed. I always goof those up.
Well, always be able to express this exponentially and always be able to express this one logarithmically.
Okay.
Okay? Once you can do that, that's going to make things a lot easier. Okay? So, what kind of specific problems would you like to look at?
Well, I was gone for almost this entire chapter for a tennis tournament. And I have a chapter test on Wednesday and Thursday.
Okay.
But I've met with the teacher quite a few times, so I feel pretty good about it.
Okay.
But
why don't you find some problems that you're not sure you know how to do, and let's go over some of those.
I got a review sheet right here.
Okay.
So also, sorry, this test, it's also over like exponential equations as well.
Right, okay.
So could we actually do one of those? Could we do 12 raised to the x minus 4 equals 4 raised to the 2 minus x?
Like that?
Yeah.
All right.
Sorry if this is a little bit of a curveball.
No, it's not. These come in two different flavors, these exponential equations. Sometimes there is a common exponential base. In this one, there is not. In other words, if this was 16 instead of 12, then I could write it as 2 to the 4th, and I could write this as 2 squared, and I'd be able to solve it very easily.
Right.
Since we don't have a common exponential base, we have to use logs to solve it. Okay?
Oh, yeah.
Now, there's 3 other rules about logs. Let me write them that are critical. The log of a times b equals what?
Equals log A plus log B.
Good. Log of A divided by B.
Log A minus log B.
And finally, log of A to the B power. And this is the killer one. I mean, this is the most.
Oh. Is it, isn't there a way, is it B to the log base A?
It's that right there. It's blog.
Blog.
I mean, it's not really blog because these letters are going to change. But it's B times the log of A. Okay? And this is the most valuable one because it's going to allow us to solve problems like this. The problem is that we don't have algebraic ways of solving this. There's no algebra that you can use to solve this problem.
Okay.
But if you have logs, you can. And the secret is to take the log of both sides. Now, you can do anything you want to one side of the equation as long as you do it to the other. So I could do the log base 12, but that's going to make it not very good over here. I could do log base 4. That doesn't make it very good over here. So I always do natural log. I'm going to take the natural log of both sides.
Okay.
Now we're going to use Rule 3 to rewrite this thing so that we can solve it using algebra. So how would I rewrite this side here?
You would rewrite it as x minus 4, would it be times the natural log?
Of 12, exactly.
Of 12. And then 2 minus x times the natural log of 4.
Okay. And notice that now we have an algebra equation. These are just numbers. You're going to get that number out of your calculator at some point.
Right.
Okay. So if I gave you this equation, minus 4 times, say, 3 equals 2 minus x times, say, 8, if I gave you this completely different equation and I said solve it, what would you do?
I suppose I would distribute.
Exactly, and then you would gather like terms.
Yeah.
So that's what we're going to do up here.
Okay.
Okay, the first thing we're going to do is distribute it. So tell me what the next line I should write should be.
We're going to have, is it the natural log?
Let's write it like that only because it's more clear than writing it like this. If I write it like this, you're not sure if the x is in the argument or not.
Right.
Whereas when I write it like this, I know exactly what I'm looking at. It's x times the natural log of 12. Even though we're used to putting the numerical coefficients in front, it's less likely to be misread by both you and anybody else that's looking at it if we write it like this. Okay, what's the rest of it?
Minus 4, is that how you would write it?
I would write it like that because if I put the 4 on the other side, again, I'm not going to know whether that's 124 or I could use parentheses, I guess. You can always put the argument in parentheses to make it clear.
Okay.
Okay, and then on the other side, what do we have?
We have 2 natural log 4 minus x natural log of 4.
All right. So now let's gather like terms.
So are all the natural logs, are they all the same?
That's all they are. Think of them as no different than a number.
Okay. So
let's gather all the terms with x in them on the left.
Oh.
And put everything else on the right.
So then we're going to have 2x natural log of...
if I take this term here and move it to the left, then it becomes this. Here's what I have on the left. Okay?
Oh.
Now I'm going to take this and move it to the right.
Right.
So I'm going to still have this that was over there plus 4 natural log of 12. Okay? Now what? Remember, I'm trying to solve for x.
Okay, so then are we going to divide?
Factor out. Divide is correct, but
yeah.
I prefer to call it factoring. I'm going to factor that x out, leaving behind what?
Natural log of 12 plus the natural log of 4.
Okay, and that's all equal to that. So
yep.
The final step
is dividing it.
Divide by that number.
So in our calculator, would it just simply be the natural log of 12 plus the natural log of 4?
Yeah. In other words, let's write it precisely, first of all. So here's our answer. That's what x is equal to.
Okay.
Okay. Now, as to whether, and you see how I got that? Okay.
Yeah.
So now the question is can we simplify that or not?
We can put the...
We can simplify.
We can put the 2...
Yeah, I could put the 2 up there, and I could put 4 up there.
Okay.
And then I can actually multiply these 2 together. In other words, the natural log of 16 plus the natural log of whatever that number is going to be the natural log of the product, right?
Right.
Same with the bottom. So we're going to have on top the natural log of 4 squared times 12 to the 4th. And on the bottom, we're going to have the natural log of 12 times 4, 48.
Okay.
Okay. And then make sure you don't make this mistake. In other words, if I have the natural log of, say, 144 divided by the natural log of 12, that is not using Rule 2. Remember, Rule 2 is that if division is going on in the argument, it changes to subtraction. If division is going on both top and bottom, you can't simplify that.
Right.
It would be only if I had the natural log minus the natural log of 12
natural log
that I could say, okay, that's equal to this.
Right.
But it's very easy to make this other incorrect simplification if you have natural log divided by natural log, which is what we have down here. The only thing you could do is put the proper numbers in here. In other words, you could square 4 for 16, and whatever 12 to the 4th power is, you could put that there. Your final answer is going to be the natural log of that number divided by the natural log of 48. And as to whether you have to use natural log, I did not. I could use any log I want.
Could you have used, just the log base 10?
I could have. What ends up happening is that these are all the same. If I have the log of 15 divided by the log of 7, that's the same as the natural log of 15 divided by the natural log of 7. It's the same as the log base 117 of 15 divided by the log base 117 of 7. In other words, all those ratios are the same. So it doesn't really matter in our problem whether I use natural log or common log. I get the same ratio. And your calculator would end up giving you the same number whether this says natural log or common log or anything else. There would be a tendency to want to solve this by taking the log base 12. In other words, if I start up here and I say, well, wow, I can simplify the left side really quickly by taking log base 12 instead of natural log. Because if I take the log base 12 of 12 to the x minus 4, the left side immediately becomes that. But then I've got the problem of how to do this. Because if I'm going to take log base 12 of the left, I've got to take log base 12 of the right.
Right.
Then I have this.
With that, are you going to have to put it in like exponential form?
No, but you're going to have to use the change of base formula. If I do it this way, I'm still going to bring my 2 minus x down on the line. So I'm going to get here. But now what do you do with this? Because that's not a number you can get directly out of your calculator. Your calculator only has 2 keys on it, base 10 and natural log, base E. So when you run into an expression like this, you have to use the change of base formula, which is that is equal to the log of 4 over the log of 12.
Gotcha.
So not,
yeah, we talked about that.
Yeah, it's not disastrous, but it does introduce a little bit of a hiccup into solving these, and if you try taking the log base 12, it's not as simple as it looks like it would be. Therefore, I don't really ever try to do that. I just automatically go to natural log, or you can automatically go to common log. There's nothing that, at this level that favors natural log over common log. Once you get into calculus, there will be. Natural log is everything in calculus. You hardly ever even use any base other than natural log. And it has to do with fundamentals of calculus. The derivative of the natural log is 1 over x, and that's huge. So I am in the habit of, when I have to solve a problem like this, I'm just always going to use natural log of both sides and then go from there. It's not any easier if I use common log. It's exactly the same math.
Right, all the
Still
steps
have to distribute everything, gather anything with x on one side, everything else on the other, factor out an x, all of that. It solves a little differently if I were to say take log base 12, because the left side simplifies quicker, but now I'm left with this right side that needs a change of base applied to it. So,
right.
All right, what else you got?
Let's see here. So for like, I don't know, there's a section on here where it's a non-calculator section.
Okay. Let's do some problems.
And
got some problems?
There's problems kind of like that, but they're like simpler logs, you know what I mean?
Okay.
But could we do one like this? So let's go like here, let me find it. Oh, here we go. 2x raised to the 1/4 equals 4.
Like that?
My teacher, yeah.
With or without parentheses around the 2x?
Without.
Okay.
She kind of helped me with it today.
These are very,
and
I can get instantly for you. Okay? We're trying to solve for x. So in order to isolate x, what's the first thing I need to do?
Divide by 2.
So now I have x to the 1/4 equals 2. And now, in order to make the left side be x, I need to raise it to what power?
Would you do the opposite, or so just 4?
Exactly. Since I take the left side to the 4th power, I got to take the right side to the 4th power. Now I can use my rules of exponents where I'm doing double exponentiation here, which means I multiply the exponents together. That leaves me with x over there, 16 over there.
Okay, that was very simple.
And it doesn't matter how complicated this is. Let's make it 2/3.
Yeah.
Okay? Well, what would I want to raise each side to?
3/2.
Exactly. Now the left side is x, and the right side is whatever 2 to the 3/2 power is. And you can get that out of a calculator also. That's actually 2 to the 3/2. Do you know what that is without a calculator?
Yeah, because this is on the part where no calculator is going to be allowed. So how would you do that?
Well,
because all I know how to do it is with the calculator.
Okay. Well, the top number is raising it to that power. The bottom number is taking that root. So I would take 2 cubed, which is 8, and then take the square root of it. And then simplify that. So that's what 2 to the 3/2 power is.
Gotcha.
Typically, the ones they give you look more like this. And when they look like this, do the denominator first. Always. I couldn't do the denominator first up here. I made this one up in my head because taking the square root of 2 doesn't give you a whole number. But the ones you're likely to get on a test are going to look more like this. And when you do the denominator first, it makes it much easier. Cube root of 8 is 2, right?
And then 2 squared is 4.
Right. Whereas if I did the numerator first, I would have the cube root of 64, and that's just dealing with bigger numbers than you need to.
Yeah, that looks a little more difficult.
Well, it's still 4. It still has to be the same answer. But by doing the denominator first, as long as that produces an integer, and it almost always does on these, then you'll be dealing in smaller numbers, and you won't have to deal with a number as big as 64. Okay? What else you got along that line? We started, I was like 5 minutes late, so we can certainly go 5 minutes over. I don't have an 8 o'clock, so.
Awesome. This one's not like that, but 8 times 16, and then the 16 is raised to 2x, equals 16 raised to the x plus 5. Are you gonna, or wait, are you gonna have to put, like, get it down so the base is a 2 for all of them? Is that possible?
Yes. In fact, that's exactly what I was going to do. There's multiple ways to solve this. You could use logs, but as long as we're looking at numbers that have common exponential bases, and 8 and 16 do, they both have a common exponential base of 2. So I'm going to write 2 to the 3rd. That's the way I'm going to write 8. Times this one is 2 to the 4th. That's 16. Equals 2 to the 4th to the x plus 5.
Okay.
Now, let's simplify the left side. What can I do with that?
Oh, gosh, this is going back to properties of exponents.
Right. Double exponentiation, we do what?
Do you either multiply or add?
Multiply. You always do one level less.
Okay.
In other words, if I'm multiplying, if I have 3 to the 4th times 3 to the 5th, that's multiplication. So that's where I'm going to add the exponents. One level less than multiplication. But if I have 3 to the 4th raised to the 5th power, that's double exponentiation. One level less than that is multiplication.
Got it.
Okay, and then when there's division going on, one level less than division is subtraction. So this is double exponentiation, so we're going to multiply the exponents. Same thing over here. We have to multiply that 4 by both of those, so that becomes 4x plus 20. Now what can I do on the left side?
Now you can condense it, so you would get 2 raised to 8x plus 3.
There you go. Equals 2 to the 4x plus 20. And now whenever you have the same base raised to one exponent equals the same base raised to a different exponent, you can equate the exponents. Now gather like terms, bring that 4x over there to make 4x, bring the 3 over there to make 17, so x would be 17/4.
Awesome.
Okay. These rules here, what I've written on this top of the page, boy, that, if you want to memorize anything, everything you see right here. Being able to convert from exponential to logarithmic, and knowing these 3 rules of logs. That's the keys to logarithms. Now, this problem right here is really not a log problem.
No.
It's a common exponential base problem. I guess it belongs in logs because exponentials are just the flip side of logs. So, because
we could have solved that by taking the log of stuff, right?
Yeah, but it's actually a little harder to do that. If I try taking the logs of both sides here, nah, that's a little tricky. I think that this probably wouldn't have been on your, this is not going to be on your test if you make that number 7.
Yeah, that looks
a much trickier problem, yeah.
Yeah.
Guess, because, see, this 2x is not acting on the 7. So I could not just take the log of both sides and then bring the 2x down. Wouldn't be able to do that. So this would be quite tricky to solve without a common exponential base, and you're not going to get problems like this one anyway. So.
Yeah, I hope not.
Yeah.
I hope she doesn't, like, make a typo and actually accidentally do that.
Uh-huh. You see any others on there that you don't know how to solve? Do one last one.
Could we do, this one's also in the non-calculator section, the log base 6 of the square root of 6.
Okay. The way to handle radicals is always to start by using exponents instead. going to write it like that.
Oh, that's how it can be written. I never thought of that.
And now I can bring that 1/2 down in front. And the other thing you want to know is that the log of b base b is always 1, no matter what b is.
So if it was the log base 17 of 17, it'd just be 1.
Yes, which means this is equal to 1/2.
Okay.
There's a couple of things that are worth knowing besides these top 3 that in other words, besides the stuff at the top. Let me just write a few of them out because these are important. First of all, that log base b of b is always equal to 1. The log of base b of 1 is always equal to 0. Why? Because any number raised to the 0th power is always 1, no matter what it is.
Ah.
So these 2 things you want to memorize.
All right.
And the last one would be b raised to the log base b of x is equal to x. So if I had 17 raised to the log base 17 of x plus 1, that's going to be equal to x plus 1.
Plus 1.
Kind of goes along
Okay.
with this one here a little bit.
Yeah, they're kind of the same.
Kind of. In other words, you want to spot wherever you can reduce stuff. And like this one here, when you have b raised to the log base b of x, that's equal to x. And things like this, what's this equal to?
That's equal to 1.
Exactly. Because that's log base e of e. In other words, that's the log base b of b, basically.
Okay.
Okay?
Yeah. Now I'm feeling a little bit better about this.
Well, good. Good. Yeah, if you need another session between now and your test, let me know.
Yeah, I might, you know what, I might just schedule one tomorrow evening.
I can put it in now if you want. I got a 7 open and I have an 8:30 open.
You know what, I am going to talk to my parents.
Okay.
And then I'm going to schedule one.
Yeah, you know how to do it online. You did it. You did this one online, right?
Yep.
Okay, cool. Yeah, I think I've changed the lead time to only an hour, so you can schedule appointments with just an hour's notice now.
Oh, awesome.
Okay. So, this log class, how'd you do in your tennis tournament?
It was interesting. I went to Alabama.
Yeah.
And it was an outdoor tournament, and it rained every day.
I was going to say, yeah, the South was hit with all that bad weather. Yeah. Snowing. Yeah.
I was there for a total of 7 days, and in those 7 days, I played 2.5 tennis matches.
Wow. Wow.
So.
What do you do with all the rest of your time when that happens?
Well, that was the thing. Every day my matches were scheduled to start at 8 a.m., and they all started at like 4:30.
Oh my gosh.
So, and once you're there, you just have to hang around in case if it stops raining.
Yeah, really? Oh my gosh. That's
so,
maddening. Yeah.
Yeah, it was, you know, I was kind of anxious to get out and play.
Yeah. When do you play your next tournament in Denver? I'm a big tennis fan. I may come out and see you if you wouldn't.
Yeah. No, you know what? I'm not quite sure, but they're gonna start getting heated back up again.
Yeah, with the weather.
Pretty soon here. The spring is a big time.
Yeah,
so.
the weather has really turned nice.
I
think it would.
So. Yeah, I'll definitely let you know when I find out.
Yeah, no, that'd be fun. I would enjoy it.
Are
you I actually looked you up online, and you're ranked #1, aren't you, in Intermountain?
I was.
Yeah, you were for a while. I don't know.
I was for a long time. Then I started to play some of the older age divisions to get some ranking points in those, because I turned 17 in June, so I've got to start aging up.
Okay.
Yeah, but you know, it's going well.
Pretty good.
Thanks.
Yeah. Okay. Casey.
So where do I find our sessions again? Is there?
Yeah. Let me give you a.
Because I remember last time you told me about the page, and then I forgot.
I've kind of changed it. Let me give you this link, and I'm going to paste it. I'm going to copy and paste it into GoToMeeting. If you open the GoToMeeting window, you should see it in the chat room. Or in the
Yep,
chat.
there it is.
Go ahead and click on that. Click on that link, save it. That's where all your sessions will be. This is my YouTube channel. Awesome. And so in order to find your session, look for your initials. You'll be a CR and the date. So like today's session, your file name is going to be CR031615.
Got it.
Notice what this day was. Pi Day. That's 3.1415. That's pi. This is one of the few days. This is the only day of the century that has
pi that's out. Amazing.
Yeah, that has pi out for 4 digits. Yeah, I mean every year has a pi day, but this year in particularly, it's correct out to 4 digits because pi is 3.14159.
Yeah, it was some kid at my school told me on last Friday. He was like, tomorrow at like 9. I don't know what it is, but tomorrow 3:14:15 at 9 minutes and
whatever the
20
rest of the digits are. Yeah.
Yeah, he's like, that's good luck.
Well, I realized that there was a date in the 1500s that was 3/14. Like 1592. So once every 100,000 years, it'll be correct out to 6 digits instead of 4 digits. But it's funny for me because my dog's name is Pi. So I had like 4 people calling me on this date, wishing me happy Pi Day. I don't know if they realized that it was more than just the yearly Pi Day, because every 3/14 is called Pi Day. But this year's was particularly impressive because of the 15.
Yeah, that's awesome. That's so funny.
Yeah. Now, anyway, this is where you can find your file. Your file won't be up here until tomorrow morning.
Oh, no, that's
It takes my computer all night to process all my day's sessions, and so I don't get them up till the next day. But they'll all go into that channel there. Okay?
All right. Thank you.
All right, Casey, you're welcome. Talk to you later.
Talk to you later.